Hi. So we're going to move forward with analysis. We know how to use Laplace to solve differential equations. And so now we're going to take a moment and kind of review where we are, but then we're going to go deeper into how to analyze differential equations or relative to Laplace, the transfer function. Because our goal is to be able to understand what a differential equation is going to do without actually having to solve it. So in the end, our goal is to be able to be a little bit lazy. But let's see where we are. Uh, you can have some differential equation. Uh, so let's just write something down. Okay, so there's a differential equation. And we know in Laplace we can basically write a transfer function almost immediately. So that'll be the output relative to the input equals, in this case, d s cubed plus uh, as squared plus bs plus c. Okay, so we know we can do that. And from our analysis, we have certain tools we can play with. We know we can take this and we can break it up into s plus, let's go with e, s plus f, because this is third order, s plus g. Okay, this is ugly. Still ugly, but anyway, we'll go with it. So when we break this down into three roots, there's various combinations that can happen. They can each be real. So we could have s plus 1, s plus 2, s plus 3 as we've had. We could have uh, two of these could be complex conjugates of each other. So 2 plus 2i, 2 minus 2i, in which case this one has to be real. So we're going to get complex numbers that reflect the roots here, where no, the real numbers are part of the complex numbers. Okay. And so from what we've done so far, we know we can determine static gain. And we're going to define it a little different now. It's simply the limit as s goes to 0 as the transfer function. So here's the transfer function. We let s's go to 0. And in this case, we'd get d over c. And this is the gain applied to a step input. So if I have a 2-volt step input, and if this works out to be a 5, d over c is 5, then I expect 10 volts out. All right? So we have static gain. Then we have roots. And so we've defined the time constant and the settling time. That's 1 over the absolute value of the real portion of what, say, lambda is a root. Okay? Uh, and we understand TS is basically the 2% settling time. We've defined if we have complex roots, we have the notion of damping ratio. And what damping ratio basically does is say, when you have second order roots, do you have a small overshoot or do you have a big overshoot? Okay, this has less damping than the other. We have natural frequency. Okay, and we're going to talk about what that specifically means, but it's in the region of the resonance, which is an area where vibrations get magnified. Let's just call it for now. We're going to get more specific about this in a bit. We have the term omega d. This is the complex portion of the root, and this actually works out to be the frequency of oscillation. So when you give a step input, we have a frequency in here. That frequency is omega d. So we've got a whole bunch of terms that we have now defined that tell us a lot about how this thing is going to respond. All right. Now, what I want to get into next is starting to understand what's happening in the top part. So if you look at everything we've had here, we also have one other term we have to have, and that is, well, I'll just call it system dominance. All right, what is that referring to? When we have these three roots, okay, if we plot them out, whichever one is closest to the imaginary axis, so we know as we go this way, time constant and settling time go up. So whichever of these poles, we'll call them, why would we call them poles? Because if s equals minus e, this whole term is infinite. So if we plot it, it's going to be really big. So these are poles. So now we have another term that we can now understand. In a transfer function, the roots of the denominator are poles, right? As these poles, complex or whatever, as they go this way, settling time, time constant goes up. This is the part of the response that dies out last, and we call that the dominant response. Okay, so a system is either going to look, depending on whether you have a first order thing in front or a second order, it'll look to be, we will then tend to have oscillation, or it'll tend to look first order, which is something like that. Okay, so what we're seeing here is that these poles, they dictate a lot, because also if they're in the left half plane, we're stable. If one lands over here, that means this is the farthest to the right. This one will dominate and the system's going to blow up. So we have stability issues that we can understand. So looking at the poles, we see they determine sort of the dominant response of the system. All right, so let's continue on here. And so we've already looked at this differential equation, and so we're going to talk about it, transfer function analytics analysis in terms of this one. So we applied a step input. So we did this, it factored into three real roots, okay? And we'll note that the transfer functions have poles and zeros. These are poles. So at s equals minus 1, the transfer function is infinite. Okay, you get infinity out, minus 2, minus 3. So that's why they're called poles. If we were to plot this thing, you'd see infinity at these 3 points. But this thing up top is called a zero. If s equals minus 6, this transfer function equals 0. So these things on top are called zeros. So here we have a 0, and then we have our poles. Now, so here's what we have. Zeros are the numerator roots, top. Poles are the denominator roots. Now here's the solution, that if we were to solve this, which we had the other day, we have an output due to the step, and then we have something due to the pole at minus 1, minus 2, and minus 3. So notice what this shows. We have a 0 here. Do you see this 0 anywhere? No, you don't. The poles determine stability and critical transient dynamics, all right? So time constant, settling times, natural frequency, damping ratio, all of these things come out of the bottom. The steady state value are critically determined by what's happening on the bottom. How this thing decays to the steady state value is really what I'm trying to say. It's largely determined by the bottom. So what do zeros do? They largely control the amplitude of the root dynamics. So if you think about this, as s plus 6 changes, A, B, C, and D can all change. So this is sort of, here you get the basic dynamic structure. These are the amplitudes for what's coming out. All right, these are what the zeros tend to affect, and strongly. So I want to start exploring the numerator a bit more. So I'm going to take this thing, I'm going to factor it a little bit. We're going to make some observations. So what is the effect of the numerator? So here's a step input applied to the system. This will get a forced response. But notice I can break this thing up. So I'm going to take the 6, and I'm going to have this, and it's going to drop the s plus here. So here's 6, 1 over s, and I just have a 1 on top. And then the s I'm going to bring over here. S times, again, here's the step input, here's the system where the numerator is just 1. So this is the same. I have an S plus 6. Here I have an S plus 6. They're the same. Let's consider these responses. All right. If I do a partial fraction expansion of this thing, here's the 6, I'm keeping it outside. 1 over S times this in time produces the following. Okay. 1/6 minus 1/2 e to the minus t minus 1/2 e to the minus 2t, 1/6 e to the minus 3t. All right. Well, let's look at this thing. Here I have this, and this piece 1 over s times the transfer function, this modified transfer function. They're the same, and I have an s in front. What happens to the response here? So if I compare this to that, here's the answer that pops out. And take a look at this. Here I had minus 1/2 e to the minus t. This is 1/2 e to the minus t. It's simply the derivative of this. Here I have minus e to the minus 2t. Well, let's just go over here. If I have 1/2 e to the minus 2t, if I take the derivative, I get a minus 2 over 2. Well, that's minus 1. Oh, derivative. Likewise here. All right, so here's what we're seeing. Adding that s, if I compared the response that I got here, and then if I put the 6 in, it just grows it by a factor of 6. But this base response, adding an s, produces a derivative of that response. S's produce derivatives. Okay, so this starts at 0, ends at 1, because I'm multiplying by that 6. If you look here, it starts at 0. If you add it all up, it starts at 0, ends at 0. It's the derivative of this thing. Okay? So let's keep thinking about that. So we have this piece here is the derivative of the response for this times 1/6. I had to make it a 1 on top. Okay, so we've seen that. Does this make sense? And the answer is, yeah, it does. We were looking at a forced response. Forced responses start from 0. So if I take the derivative of the forced response, I'm going to get s f of s minus the initial condition, which for the forced response was 0. So this is a s of s minus 0. All right. Adding a numerator into the s is simply adding a derivative to the forced response. That's what it does. So this brings up the question, well, what is adding 1 over s? Actually, it's an integration. And that makes sense. So we have s, the inverse of differentiation, integration. So we'll test this. So here's an impulse. Okay. Now picture passing an impulse through an integrator. So, okay, so the area under the curve as you move along is 0, 0, 0, 0, 0. And then at time 0, the area under the curve becomes 1. And thereafter, we add no more area under the curve, so as time goes on, the remaining area is 1. A step is the integration of an impulse. So adding a 1 over s into the bottom, it's a step input, it's also an integrator. A step function acts as an integrator. Fascinating. Okay, or maybe you don't find it fascinating, but it's how it works. So here we have, recall here, the Laplace transform of an impulse, unit impulse. Delta t becomes delta s. Go through the math, it's a 1. The integral of a step is 1 over s, but if we actually do it by the math, here's the Laplace transform of unit step. We'll call that u of s. Go through the math, get a 1 over s. So there's an integration that happens. Okay. So continuing, what happens if I were to add an s squared into the top? Okay, well, this says relative to the response you get for this piece, adding an s squared says add the second derivative of when you apply an input to this, there's a forced response. Okay, that's the 1 over s. Put an s squared up here. It says relative to what you have here, take the second derivative and add it in. Okay, now we need to bring up another point here. When we add zeros, what happens if we put zeros that are close to poles? In fact, we kind of did that right here. We have an s squared here, we have an s. They cancel. So this would actually be this s, and one of these s's would cancel, and I'd have 6s over this piece. Okay, zeros can cancel poles. So keep in mind, they are affecting the amplitude that the pole would provide. So in other words, they can drive the amplitude all the way to 0 and eliminate the effect. So that's kind of interesting. So let's just look at an example. Transfer function equals 8 over s plus 2, s plus 4. All right, we apply a step input. All right, and so here, this is the response. 1 minus 2 e to the minus 2t e to the minus 4t. So we take, here's the transfer function, add an s in the bottom, that's applying a step input. We do partial fraction expansions, and you will wind up with 1 over s, 2 over s plus 2, 1 over s plus 4, which we can, 1 over s becomes a 1. 1 over s plus 2 would be e to the minus 2t, and then we have the minus 2 that goes out in front, and then plus 1 e to the minus 4t. Now, let's add in, so we have an 8, let's put a 2s in front of it. Okay, I can rewrite that as 2 times s plus 4. These will now cancel. So this is the effective system. This has been canceled. So we would expect the response, here's what we'd have. We expand that out, we get the following, which is 1 minus e to the minus 2t. And we see this piece is now gone. All right, and if you look here, we had 1 minus 2 e to the minus 2t, so this has been cut, right? So we're seeing zeros affect amplitude of the pole response, and they can kill poles. However, there's an exception. We have one exception we have to see, okay? So while they can kill pole dynamics, we have to take note that if you had a pole, let's say we had an unstable system. So we had a pole at positive 2. This wants to blow up. Well, here's the problem. We cannot cancel this because it is impossible to put a 0 on and have that match up to the 0th decimal point. All right? So if we put a 0 over it, we can slow the speed down at which the system blows up because we can affect this piece. However, we cannot fully cancel that. You will always somewhere at the millionth decimal point not quite get it completely, and the result is the system will eventually have this thing dominate and it will blow the thing up. So you can never cancel an unstable pole. And we're going to leave this. We still have a little bit more zero discussion to do, but I'm going to stop it here, and I'll talk to you soon.